Welcome to another week of learning with Mrs. Hasegawa. So remember last week where we began to evaluate which model of matter, particle, or continuous could better explain observations of mixing liquids. And I was mixing water and acetone together, and we discovered that when we mixed those two liquids together, the volume decreased. And we were exploring which model of matter helped explain our observations. So we have the continuous model, which is described by the ancient philosopher Aristotle way back when, to around 400 BC era, and he explained that matter is continuous. All materials all around us can be divided into smaller pieces forever and ever and ever and ever. And those smaller pieces act the same as the whole piece. Then we have Democritus, who is around the same era, and he disagreed. He came up with the particle model, saying that matter is made of tiny particles and they cannot be divided forever. There's going to be a point when you cut paper, rock, grain, whatever, and there's going to be a point when you keep cutting it, you're going to get to the smallest part that cannot be cut any further. It's not continuous, it's finite. So those smaller pieces or particles have different properties than the whole piece. So in this activity that I'm going to be going through today, we're going to gather more evidence to support one of those models of matter by exploring the additional phenomena. So this time we're focusing on the behavior of gases. So we were focusing on the state of matter of liquids last time, and states of matter are just the forms that matter can take on. So let's go over a little bit of vocabulary before we move forward. So matter. Matter is anything that has mass or takes up space. So I'm matter and I matter. You're matter and you matter. This table is matter. This whiteboard is matter. Everything that takes up space and has mass is matter. And mass is the amount of matter or substance that makes up an object. And we measure mass by using a scale. And so something that's unique with mass is that the mass that you have here on Earth will be the same mass that you have, say, on the moon. So your mass never changes. Then we go over particles. So particles are the tiny pieces that make up matter. It's a very broad term, so it's covering all the tiny parts, all the tiny pieces that make up matter, that make me up and you up and this whiteboard up. Those are particles. So back to our models of matter. So we thought about these two models in regards to liquids with the acetone and the water. And like I said, now we're going to think about how these models hold up when we're looking at gases. So we're going to be exploring the question, are gases matter? Is air matter? So in order for air to be matter, it must have mass and it must take up space. So looking up to see if it takes space is easy enough. I can do that simply by using a balloon. So as we can see, I have two deflated balloons. They're not floating anywhere. They're pretty small and they fit in my hand. So air is all around us. It contains many different types of particles, oxygen, carbon, nitrogen, all these kinds of things. And we have air in our lungs. So I can blow air into the balloon. So right now, this balloon is not taking up much space. It does have a mass. It does have some kind of weight to it. So let's blow up the balloon. Ta-da! I blew up the balloon. So I'm not blowing it up very much. Let's see if I can tie it off pretty easily. So now we have an inflated balloon and a deflated balloon. This one, which has air in it, takes up more space than the deflated balloon. And what did I do? I just added some air. So, does air take up space? Yes, my friend, it does. So let's move on to the next part. I'll put these aside. I'll put these behind me. So, does air have mass? So in order to measure if it has mass, I'm going to use something that makes it a little easier to measure and put that on a scale. The balloon's a little hard to put on the scale. So in order for me to do this experiment, I'm going to be using a 16 milliliter syringe, a stopper, a cap for the syringe. It goes onto the top like so. I'm using some water. I'm going to be using some water for this experiment, and a scale. So I have to make sure that the scale that I'm using has a precision to the 100th decimal, because most likely if we measure air and if it has mass, it's going to be really small. And so we want to make sure that our instrument is able to measure that small amount. All right, so let's get started. So I'm going to take the syringe and I'm going to make sure that it's empty. So I'm going to take the plunger and make sure that it's all the way in. And as we can see, when I pull on the plunger, I have to pull it in and out like so. So now that I push the plunger all the way in, I'm going to put the cap on it to make sure that nothing goes in and nothing goes out. And essentially what I'm going to try to create is kind of like a vacuum, which means that there's going to be no matter inside. It's not going to be perfect because this is not the most scientific pieces of equipment, but I'm going to pull it all the way out, and then I'm going to use this other piece of material I forgot to mention, sorry about that, is a nail. Well, then to this case, it's a screw. So I got to pull it out, and I got to do this sitting down because it's kind of hard to pull out, and then I'm going to put the nail in as a stopper for the screw. So let me do this. So I got to pull on it. And there we go. So now I'm going to measure its mass. So I'm going to turn on the scale, and I'll put the syringe on there, and it weighs 41.27. So since we're doing an experiment, we need to make sure that we write down our data. Mass is measured in something called grams. So the mass of the sealed syringe, it's sealed because it has the cap on, is 41.27. 41.27. Now I'm going to take the cap off, let some air in, and see how much it weighs. You can hear the pressure and hear the air going in. So I got to measure it with the cap, because I measured it with the cap last time, but it is open. And now it measures 41.34. Grams. Not to forget our units. So now let's look at this. The open syringe, which is this one right here that I just opened. So does it have more mass than when it was sealed, less mass, or the same? Got 41.34 versus 41.27. I would say it's more. So the open syringe has more mass. So what does that mean? Is gas matter? Is air matter? It takes up space, as we saw with the balloon, and it has mass. So that means that air is matter. Ta-da! Air is matter. So, as we're looking at this and thinking about this demonstration, if you were to draw a model of the air in the syringe that explains why the mass of the syringe when the stopper was closed differed from the mass when the stopper was open, how would you draw that model? So how would you draw a model showing the differences of when the syringe was sealed and I pulled the plunger out versus when it was open and I let all the air in? How would you draw that? How would you draw the air particles inside before and after? And how would you use your model to explain these observations that we just saw? What would you draw? So let's study this some more. So I'm going to take out my stopper, and I'm going to fill the syringe with air. It's already filled with air, but I can do it again for show, filling it with air. Put the cap on, and now I'm just going to try to push the plunger. So as you can notice, I can't push it all the way in, but I can kind of push it in. So what do we notice? You notice that I can kind of push the air. I can compress or push the air. So how would you draw a model that explains what's happening here? How can I draw something to show that I'm compressing the gas? What's happening? Why can I compress the gas? What do you think that happens? So now let's do the same. But I'm going to pull the syringe all the way back to the beginning, like I did at the beginning of the experiment, and put the cap on. And now I'm going to try to pull it. And as you can notice, it's hard to pull. And when I let go, what happens? What do we notice when I let go of the plunger after I pull it out? It goes back in, right? And it makes a cool popping sound. So the last thing that we're going to do is we're going to fill the syringe with water. So I'm going to fill it with my little cup of water right here, just a little bit. The measurement's not important. I'm just going to fill it with some water. And then I'm going to get all the air out. And I'm going to put the cap on. So now I'm going to try to push the plunger down to see what happens. Do you think I'll be able to compress it like the air? Let's see. It looks like, if you can look at this, I'm not able to press it at all. And I'm trying. So how could we draw a model that can explain this? How could we draw a model that represents air being compressed versus water being compressed? What's the difference? Here's me trying to compress the water, and I'm not able to. Why do you think I can't compress water? I can compress air. So one last time, I can't compress the water. Let's show the air again. So I'm going to fill it just a little bit of air. Put the cap back on to seal the air. And now I'm trying to compress the air. So unlike the water, I can compress it. Why do you think that is? And how can you draw a model that represents the air being compressed versus water being compressed? Why can we compress air and not water? What's between the air particles that's allowing this to happen, do you think? All right. All right. That is the demonstration for today, and that's all for this video. So in conclusion, we decided, is air matter? Yes, air is matter because number one, it takes up space and it has mass. We found that the mass of the open syringe with air in it weighs more than the mass of the sealed syringe. So air is matter. So let's look back at these descriptions of models of matter. So does the continuous or the particle model best explain this demonstration? What do you think? Do you think air can be continuously cut forever like Aristotle describes? Do you think the small parts of air are the same as the bigger parts of the air? Or do you think air cannot be cut much smaller than it already is? What do you think? Until next time, I'll see you later. Bye.